Hello AS Math, it's Mr. Knight, yet again. My sister's back in town, so you're probably going to be seeing more of her in the future, if you saw the last video, so that sucks. Anyway, we're not going to focus on that today. We're going to look at geometric series and infinite series. We have already looked at arithmetic series and how you have a nice little formula to add up any arithmetic progression and get whatever total you're looking for. You can do the same thing with geometric series. Here are the skills today, and here is very brief vocab. Before we jump into geometric series, it is story time right now. Okay, we're going to talk about the origins of chess, which is one of my favorite games ever made. Certainly my favorite board game. How does the story go? And you do not need to write this down. Please don't. So the Emperor of China was actually impressed with the inventor of chess. There's a lot of people that believe that chess was invented in China, and so the story goes that the inventor of China approached the emperor, and the emperor was like, "Hey, man," probably wasn't like, "Hey, man," but he's like, "Hey, man, what do you want? You can have anything. Anything in the world that you'd like. You have made an incredible game. What would you like?" And the inventor said, 1 grain of rice for the first square of the chessboard, 2 for the second square, 4 for the third, 8 for the fourth, and so on until the final square. So how much rice did the inventor really ask for? By the way, the emperor was like, "You got it, dude. I'll give you whatever you want." And so the inventor walked away and chuckling to himself because he knew exactly what he was saying to the emperor. The emperor, very nice guy, a little naive, didn't really grasp geometric progressions very much, and so we're going to help out the emperor a little bit, see how much rice this inventor really wanted. So, if you're unfamiliar with a chessboard, okay, let's take a gander of how big a chessboard is, okay? So if we're looking at a chessboard on Amazon, no less, okay, it is 8 squares by 8 squares. So there's a total of 64 tiles on this. And again, he wanted 1 grain of rice for 1 square, 2 for the next, 4 for the one after that, 8 after that one, and so on and so forth. So it's doubling every single time. So let's take a look at that mathematically. Let's see what's going on. So if I have 64 terms, because I have 64 tiles, if I have 64 tiles, that means I have 64 terms, and it's doubling every time, so r is going to equal 2. That's my common ratio, and so if we're adding all these up, that guy is going to get massive in a hurry, okay? Even just me doing 2 to the 63rd is pretty substantial, let's put it that way. Okay, that is a huge number. So this is how we can actually figure it out. Now, this isn't going to be, again, don't write this down. You'll write it down when we get to the actual formula because we're building towards it. But we have this first series, we're going to call it S, and it's pretty much what we had up here. But now I'm going to multiply this guy by the common ratio of 2. So that's going to give me the second equation. I'm going to label that equation 2, and now we have 2s equals 1 times 2 is 2, 2 times 2 is 4, so on and so forth. I doubled everything, okay? And if I double the 63rd, I just go up 1 power, so I have 2 equations, and now this is what I'm going to do with them. I'm going to subtract the first one from the second one, and I wrote it like this. I'm going to break down why. Because I'm subtracting, I kind of rearranged it like this, because what's going to happen is if I subtract these, this is going to turn into -1. This is going to be -2, +2, so those would cancel. And then this would be -8 and 8, so that would cancel. And -16 and 16, that would cancel. And you can see what's going on. The 2 to the 63rds would cancel. And I'm left with this. I get S equals -1 plus 0 plus 0 plus 0 all the way to plus 2 to the 64. If you remember from algebra, that's basically this guy just did elimination. And so using elimination, we could actually get left with 2 to the 64th minus 1. And if we throw that into our calculator, I'm just going to do 2 to the 64. And we get 1.84 times 10 to the 19th power, which, let me try and put in perspective how big this number is. There are probably less grains of sand on the planet than there are of grains of rice that this guy was asking for. That is how massive this number is. To put it in even more perspective, to get to a billion, it would be 1.84 times 10 to the 9th power. And we are 10 magnitudes over that. We are not in the trillions, the quadrillions. We are in the quintillions, past that even. Sextillions. We might be in the septillions. It's a big number. You get the idea. Massive number, okay? Well, there needs to be a formula, a way to actually do it, and to do it consistently. And to save us a lot of time of deriving it, I'm just going to give you guys it, okay? Are we cool with that? This is the sum of a geometric progression is equal to a times r to the n power minus 1 over r minus 1. Or you can actually write it like this, where the 1 and the r are flip-flopped on the top and the bottom. And those are your geometric series equations. So you only need your first term and your common ratio, and you can get any sum of geometric progressions there are. So now let's use it. Let's see how to use it. So this is scale 1. I want us to find the value of 0.2 plus 1 plus 5 plus whatever to 10 terms. Okay, so if we're labeling this, we know that a is going to equal 0.2. My n is going to equal 10. There's 10 terms. And to find r, I take 1 divided by 0.2, and I get 5 as my common ratio. So using one of these formulas, and I'm going to go ahead and use the top one, we're going to 10 terms, so S10 equals 0.2 times 5 to the 10th power minus 1, and that's going to be over 5 minus 1. So again, working this out, let's clean it up a bit, just a bit. Let's go ahead and let's calculate that. We're going to throw it in our calculator. So to do this, I would work the inside part first. I would do 5 to the 10th power. Take off your 1, because it does matter. You're going to multiply by 0.2, and then finally we're going to divide by 4. And we get 488,281.2, which, yeah, I would not have guessed that in a million years. Maybe some of you would have guessed that if you have superpowers, which, in that case, it's kind of a lame superpower. What are you doing with that superpower? Just kidding. I'm not here to judge superpowers. I wanted to be Spider-Man when I was a little boy, and that still hasn't happened, so I don't have superpowers. At least you have superpowers. Well, now I'm sad. But that's how you use the sum of a geometric progression. It's a lot of plugging and chugging, and we're going to get more work in class with your homework on actually using it in other situations, okay? But I want you to get the gist of it. So now, let's move on. Let's consider a paradox. It's one of my favorite paradoxes. It's the race of Achilles, okay? So if you remember, I don't know if you watched Hercules, the Disney movie, or if you know Greek mythology, but Achilles is a famous fighter and warrior in Greek times, famous in Greek mythology, and he was also a heck of an athlete. So he ran this race. It was only 2 meters long, really short race. Here's the problem, though. He decided with his race he was going to do something different. He was going to run half every single time and try to finish this race. So he ran 1 meter, then he ran half of that, then he ran a quarter of that, then he ran an eighth of that, then a 16th, then a 32nd, and he got really, 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 really close. Did he ever reach the finish line? Well, if he's doing it like this, he's actually never going to, and we're about to see in a second. So first of all, let's say our common ratio, 1/2 divided by 1, that's just 1/2, or 0.5. And we know a is equal to 1, that's our first term. And we didn't really get how many terms we were adding, so let's just say we were going to go with 4. So S4 equals 0.5 to the 4th power minus 1 divided by 0.5 minus 1. I would like you guys in your calculators to calculate that. And I am going to do the same. Oops. Careful. If you made a mistake like I did. So I did 0.5 to the 4th power minus 1, and then I divided by negative 0.5. I didn't do that the first time, and I got a negative answer. But we should get 0.1875. Okay, that's good. What if we tried 6 terms? We could do it that way. So again, we are going to do 0.5 to the 6 minus 1 over 0.5 minus 1. We do the same process again. And I got 1.96875. So clearly he's getting closer and closer to 2. Really, really close to 2. But he's not really getting there. That's weird. And that's after 6. And really, guys, if we tried this forever, this is what makes it a paradox. We would actually never get Achilles to finish the race. And as amazing of a warrior he is, his math skills needed some work because he thought he could defy mathematics in the abstract, but it didn't work out for him. And as you can see, the more terms we take, the closer and closer we get to 2. In fact, as n approaches infinity, the sum will approach 2. And we have a special name for that. The sum to infinity, being a finite number, means that that series is convergent. Convergent is when an infinite series gets closer to a finite value, in this case, 2. And definitely remember that, because I might ask you on your quiz, wink wink. But what about something like this? What if we did this same process, but forever and ever and ever for 1 plus 2 plus 4 plus 8? What happens as my n approaches infinity? Okay? Am I going to get a sum? Well, if you think about this, if I keep adding those numbers, there's no limit to how many terms I can add, so this guy is going to also approach infinity. And in fact, we call this type of series divergent. It's an infinite series that becomes infinitely large, and it's actually an indeterminate form. Infinity isn't a number, it's really a concept, and we're not getting a value out of this. Convergent, we are. Now, what's the difference? How am I able to do it here, but not here? And the answer lies in our common ratio. If our common ratio is between -1 and 1, then we can actually have an infinite geometric progression and actually get an infinite series that converges. And the formula for that, if it can converge, is S infinity equals A divided by 1 minus R. Okay? And that's kind of the key right here. If this guy is, less than -1 or greater than 1, it's going to turn into this, and we can't actually do it. But let's stick with an example that we can do. Let's find the sum of an infinite geometric progression. If I have this sum right here, 0.2, 0.02, and 0.002, first of all, we know A is 0.2, and we know our R can be found by taking the next term, dividing by the previous term, and that should be 1/10. But you can always double check in your calculator, and I got 1/10. And awesome, because it's between 1 and -1. So now I can actually do this. My A is 0.2, and I have 1 minus 0.1. So this is 0.2 divided by 0.9. And if you put this in your calculator, or if you're really good with decimals, you should see that this is, well, 0.22222, also known as